formed steel, which I decided to call it cold formed steel recently because the other people call it light gauge steel. The architecturals and structurals call it cold formed metal framing. People call it metal studs. But the reason I chose cold formed steel is Cold Formed Steel Engineers Institute and CFS Designer Software, kind of all honing in on CFS as the terminology, and it has nothing to do with the CUFSM. Some history: the American Iron Association was formed in 1855, and that was what becomes AISI. Popularity started in the 30s. First edition of AISI was in 1946, which all this stuff is pretty recent, in the terms of the time on the earth. SSMA was created in 2001. CFSEI, which is the Engineers Association, was created in 2006. And then just recently, I discovered, I believe there's a new AISI S100/24.
That we need to get.
And figure out what's new in it. I tried to find two houses that looked alike, one wood, one steel. It's very versatile, using light gauge steel. It's increased strength, faster construction, it's resistant and fire resistant. And then there's traditional wood framing on the left versus cold formed steel framing on the right. Traditionally, you have studs in the light gauge steel. Headers. The top track is typically a double top plate in wood, and steel, it's just a single track. The bottom plate is just a single track in light gauge steel. This isometric kind of gives you an idea of some box up headers, but I can get into some more of that. Typically, everything is either screwed or welded. They'll do one or the other on the site, not both. Here's the available depths and available widths and gauges. You can kind of make anything you want out of a flat sheet of metal, which is how all this is formed. It's just taken from a flat sheet of metal and rolled.
Do you find that there are more contractors out there that try to form their own studs, or do they purchase them from a manufacturer?
Yeah, everyone I know has been purchasing from a manufacturer, but one benefit of us doing engineering for drywall contractors, they can shop it then. Otherwise, if they go to Clark Dietrich, they get engineering from Clark Dietrich, and this way you can provide them a value engineering aspect. But here's a stud. It's formed out of a flat sheet and a track that stud fits in. And this is a deflection track, which will go on the top and allows deflections to move. But be careful, they're sharp.
Yes.
One thing about the available gauges is they call it out as 43, which is the mills. 0.0043 is the minimum, but the design thickness there is shown there. And next slide will be a quick one.
Do manufacturers vary in the, between the, the manufactured real thickness and the minimum?
I don't think so. I think everyone holds pretty much to the design thickness.
Okay.
And this is where I usually refer to get the steel thickness. If you guys, that's very similar to the spreadsheet. We have that table listed for design thicknesses for light gauge steel. The SSMA group is a great place to go to for information on studs and all the technical data. Next sheet. This is a typical cover sheet from one we did an example for. It's got a lot of data, a lot of notes. It's got the fastener data and the cold formed steel frame profile information. Next sheet, I get into a little bit closer up. These are the different profiles you can have with light gauge steel. A stud is an S, a joist is a J. Joist does not have punch outs in it. Then track is T and so forth, as you can see there. On every sheet, on every project, we list all the available studs that were used. So as you can see in the list, there's bridging, there's angles, there's track. It's kind of like when in the back of our curtain wall calcs, we list all the profiles and provide all the profile information.
Hey, Chad.
Hey, Chad, real quick on
Yeah.
go ahead, Matt. Okay, thanks. No, yeah, I was gonna ask about this, the nomenclature. I've seen it many times, and it's always kind of confusing what numbers go where. So can you dive a little bit into how the naming of it, what part tells you what, and is it in inches, millimeters, what, like a little bit more about the naming conventions?
Yeah, I guess I skipped over the key there. The nomenclature is remember, depth is the first three numbers, and then the letter is the type. The next three numbers are the flange width, and then it's a dash 54. Like a dash 54 is 54 mils minimum, but it's 0.0566 if you look at the table and find a 16. So if you have a track, it's a 600T, and then the flange is only 1.25 inches, so it's a 600T 125. So that's 6 inches deep, 1.25 inches tall.
Hey, Chad, it looks like the 600 and the 162, if you stick a decimal point right behind that first number, is that essentially what it is in inches? So 6.00 inches, 1.62
Yep.
inch and 5/8. Are you still wanting the sheet?
No, I guess the next sheet. That's right. Anybody else have any questions on that?
On the studs, what's the reasoning for the punch out?
That's to provide lateral bracing and to run electrical wiring and stuff like that.
And
But,
the steel grade wouldn't be listed on the name, right? Like, you know that for certain gauge ranges, you use grade
Yeah.
33 or grade 50, right? That's something
Yeah,
that the structurals give it.
Yeah, usually 16 gauge and heavier are 50 KSI. So there's some standards there. If you had like something, a 2.5 inch stud that you needed to be 50 KSI, then you would list it out and add that 50 in the parentheses.
Okay, thank you.
Now, here's our different styles of headers. Header style A on the top is boxed. There's some screw options and some welding options. Header style B is back to back, and that's for load bearing, so that the loads are transferred axially. And then there's header style C, which is pretty simple for over single doorways and stuff that doesn't need to carry that much axial weight, dead load.
What do you find more prevalent, the screwed headers or the welding?
Yeah, the screwed is I'd say 90% of it. Welding light gauge, I don't like it. It's so thin,
Yeah.
you know. So we put it as an option, but I think the guys in the field, they just want to screw stuff together, go.
Yeah.
But same thing, like we have header schedules and summaries. We have a header schedule and jam schedule there where we call out the different styles and how many members are in each. So I guess next slide. Here's our fastener schedule. Typically, the framing is screwed together with 8-inch hex screws, or number 8 hex screws. Structural connections start with number 10 or number 12 hex screws. But the frame to frame is number 8 or 1-inch weld. We use hex screws and a lot of PAF fasteners, powder actuated fasteners. So they're shot in. So a lot of the track goes down into the concrete with a shot in PAF. And then some heavier anchors for kickers and shear wall hold downs and stuff like that. I guess now I'm just going to get into some basic framing to show you guys. This is a framing under a beam, whereas you see in it comes from AutoCAD Mechanical, so I lost a lot of information. But you see the beam up on top, there's a gap. I'm calling out a 3/4 inch gap for deflection. And then it's shot in with a PAF, 1 per stud. That D, and the E is another one that's a PAF at the sill. And the section on the right is a window below the beam. And they've got jam anchors at the jams. A lot of things got lost here because of conversion to pipe. But then,
Whenever you're designing anchors that are powder actuated fasteners, do you use Hilti alone? Is that?
yeah, I always use Hilti. I even use Hilti for eccentric screw horses.
Yeah, yeah.
But, yeah, Hilti is kind of the number one source. Next slide, I'm just going to go through some different types of framing styles. This is a spandrel panel. This gets dead loaded at the floor slab. Then it's got a kicker, usually 4 foot on center. So in this case, you usually have to design the bottom track to be able to span between the 4 foot on center kickers.
How long is the typical longest header that you can have at from steel? How far have you seen them go?
Boy, not too far.
maybe
Boy,
18 foot?
Yeah, I'd say 16, 18 feet, somewhere in there.
Question, is there a, I think I remember hearing somewhere that there was a like minimum 4 fastener connection somewhere in like the code or something. Do you know anything about that?
I know a minimum 2 duplicity they call out, but I don't know about a minimum 4. Talk about that.
Javier, did you have a question?
No, nope.
Okay.
Right, I guess next slide.
Does someone else have a question?
Here's some examples of load bearing. The section on the left is parallel to the structural framing. And it just has a C section screwed to the studs to carry the roof deck. But the section on the right, that's the true load bearing wall. In this case, they had a tube steel distribution header that ran continuous to take the load from the steel joist out, spread it out more to the studs. But I made them add a steel plate. If you look where the steel HSS comes down on top of the metal studs, there's actually a gap in there, and that can cause it to fail and sag. So to get a true distribution header with the HSS, because of the rounded corners, you got to add a steel plate to the bottom to really distribute it out to the flanges of the studs.
That's what that weld sign is up there?
Yeah.
Or the weld on a steel plate?
Yeah, they had to add a steel plate there, which is some little tricky things you got to watch for, because it's such like it's steel that.
And that's needed to distribute out the load from the HSS
Yeah.
number better?
Yeah,
Is it just simply, does it go out farther than the HSS, or how does that?
well, I think, from the load of I did an analysis for the HSS loading and reactions into the studs. But the general, well, it takes
Rounded.
45.
Yeah, the rounded shape, yeah.
So load bearing is far and few between. It's not that often, but it comes up. Then here's some shear wall framing. This was a small bank. So it's a single story, and you can see the diagonal strapping. We got another table to call out what is required. In this case, there was 2 5-inch by 16-gauge straps, and there's like 14 screws at the head. And at the bottom, we use a Simpson hold down. Just on the left side of that shear wall, you can see another side section. You can see where there's a W14 beam that we're picking up that's load bearing up to some jam studs.
Do you find that the structural engineer record pretty well defines the shear walls?
Yeah,
The
yeah, and the loading, usually they'll put all
loads on there?
yeah, which is nice because you can double check it and work backwards. I guess next drawing. There's all different types of framing. You can do soffit framing. There's a knee wall there. That's something we're familiar with. If you have a window with a door and you got that corner right there, it's a knee wall. That thing has to take the moment from the window above. So that's one thing that happens a lot. And I call out these days Simpson connections or equal or equivalent because they are so well developed in their details and their design, kind of like Hilti with their anchors. Simpson is quite involved. And they are the ones that run the software, the CFS design software. I show you some of the design software here. These are the outputs. You can have simple span with parapets. You can do your shear walls. It spits out all the data for you if you enter the information right. It's a pretty thorough software. The next sheet is just some more of that. Size your door openings, your window openings. They'll even tell you the anchorage to use at the bottom studs, and it's very, very thorough, and everyone uses it.
Yeah.
So
Hey,
there's other
hey, Chad,
applications.
does it take you to the AISI section that is checking for the lateral torsional buckling or other failure modes?
Yeah, I believe you can go into yes, it does. You can go into
Okay.
each member and go into
The code check for it. Like similar to what Rita does with some of our regular tubing or other steel shapes.
Is there output drill down, or is it just in the program that you have a drill down? In other words, in the program, do you have to click on the member to get the full?
Yeah, I think in the output,
But in the output, I think it's just flat. You can drill down in that.
Yep. Yeah, I get what you're saying, yeah. But it's pretty simple to use. Other structures, unique structures, steel panel systems, modular construction, doing panel drawings and prefabbing panels in the shop. Some things that show roof truss systems, floor construction and whatnot. But other sources, if you are looking for info, is that new AISIS 100-24, gotta figure that out. But the SSMA website is a great place, and so is the Simpson and Clark for framing connections.
Thank you for sharing that.
If you guys would just brainstorm with me for a minute and think in the terms of features and benefits, because a feature is like, this cup has a handle. We provide cold form steel drafting and engineering. But the benefit is, if this is hot, then I'm not gonna burn myself. So the feature is what we're providing. The benefit is what is the value of it to somebody. So we can think in terms of that. What are some features and benefits about cold form steel that we offer?
I think one of the benefits from our drawings is they could build off the drawings. They can use the dimensions that we provide to cut the studs to, if it comes to approved from the architect, they don't have to figure out stud lengths and all that stuff.
And who is they?
The drywall contractors.
A drywall contractor. Okay, what else?
One distinct advantage is we're always doing panel design and we're always counting on girts to be able to connect back to cold form steel. Wouldn't it be nice if the same designers of the cold form steel were the designers of the girts and the panel to make it line up? Because right now, out in the field, we don't know if it lines up. We're just saying, hey, you got to have a cold form steel there, support. But we don't know. And so wouldn't it be nice if everything was in sync and we knew exactly where cold form steel was that we were connecting to?
If we have BIM, we can just integrate everything, like put the 3D in the drawings. And you know exactly where it is located. That is one benefit here.
So you have the team?
Be nice to have the BIM.
The beam.
Model. So if we have that software, then yes, it's a great deal for us to be able to do that, because we can tell them, oh, this is the length. There is nothing here. There's one difference for the finite element analysis. When you have that, let's say channel, yours is the IX, IY. Like finite element is when you drill something and you have a hole beside it, how much of a stress it of the failure, because it will create like 60 degrees, failure on the system based on the holes and based on the edges. So there's a big difference between, your design and the finite element. But I think, we can have that benefit if we can put that model inside the drawing, like really see it.
Yeah.
All right, go on, Javier.
I think it follows the same line of what we've seen happen with the shop drawings, that it gives us a lot more control of the product that we're delivering, and it gives us a lot more power of showing what we need to show on the drawings, and especially for building movement. Every engineer and drafter in this call has had the sometimes excruciating task of getting the building movement out of a project. Like Chad show, if we can clearly detail headers and mark them where they occur on the drawings, maybe integrate that into the shop drawing, so it's not this disclaimer note that we put in the shop drawing saying, we're assuming a header, please contact JEI. If there is not, I can bet you that 90% of the times we don't get contacted. They just run with it. So no, I think it's a great additional layer of controlling what we're providing. And we'll be, and this is more of a question to you and Chad, glazing contractors don't really get into it's more, who would our clients be? And what are the novelties or challenges of dealing with that whole new universe of clients? We're used to glazing contractors and we can handle them. But what would you say are the biggest challenges for this other brand new set of clients?
Yeah. I think that's a great question, and I'm gonna answer that, and then I'm gonna go to Chad, but here's, the structure of a contract is you have a general contractor, and they go out and they get the subcontractor for the glazing, they get the subcontractor for the framing and the chipboard or the drywall.
Yeah.
And so there's two separate contractors that they kind of deal with there. What if they're both coming to us? That's great.
And the customer base is typically drywall contractors, metal stud framers, interior drywall guys. No real work with architects or other engineers unless there's something going back and forth behind. But yeah, it's all drywall contractors.
Are you saying, Javier, if we're doing the cold form steel and we're calling out issues around building movement, that when it gets to the glazing contractor, we've minimized that whole section of RFIs that we normally have to do? Is that what you meant?
Yes. I would say the most common time dragger for a project that kind of like leaves us waiting is a proper response to an RFI. Now, there's still some cases where we will need that RFI when we're anchoring to the underside of a concrete slab or a steel beam, but the majority of projects will be anchoring to cold form steel. So if we're involved in a project that we're also doing the cold form steel, we wouldn't need that RFI anymore.
Yeah. Hey, Vicky, do you have any experience with cold form steel or any thoughts about cold form steel from your background?
I've only done a little bit of it as far as just some infills I've done, but then I've also done a curtain wall where there was like a green roof or like a live roof above, so there was like 3 inches of movement. So they ended up like taking some of that out in the header of the cold form steel where they did like a slip connection, just so that you didn't have to take like a 3-inch caulk joint at the top of your curtain wall. So they kind of worked with doing like a slip track to take some of that movement.
Yep.
Yeah, good.
There's one other great advantage that I see, and I'm kind of waiting. Can anybody guess what it is? Okay, here's what it is. The future is moving towards unitized construction for facades. To get that unitized construction, there has to be a structural element there in the facade for the panels to fit onto, and that is going to be cold form steel. So we're strategically positioning ourselves in a prime spot to be able to be in that part of the industry.
Yeah, I think the future of the steel industry too is going to be strong. I mean, that's the recession hit and everyone stopped building with cold form steel and went to wood, but now you see it's back everywhere. And
Yeah.
I think the price point is coming back around. Hopefully.
Can I share a little bit of your experience with that?
Yeah, we had a client that had a custom window system that used steel, light gauge steel, instead of aluminum. So we had to do a lot of different analysis on that. I had to read through the AISI to find out how to analyze that one. That was unique.
Yeah.
Yeah, that one forced us to dive deep on the ASI and find the right lateral torsional buckling. And these shapes were wild. They were folded pieces that would fold onto themselves to shape the form of a mullion. But
Massive
was a
thermal breaks between.
Oh yeah, I kind of forgot about those. But yeah, the biggest thermal breaks we've ever seen, like this thick, and law is almost 50% the depth of the mullion. So yeah, Kevin killed it on that one. But yeah, it allowed us to dive deep. We didn't really use any software. Kevin, remind me, I think put together a spreadsheet, right?
Yeah, and I used CF Sim to it. And then I ended up just writing a bunch of formulas in Word to come up with all the calculations from AISI.
Yeah, and the reason why we didn't use the Simpson software was because, like as we see in this industry, a lot of shapes are proprietary, and you can't really put them as shapes in this type of softwares. With conform steel, they're a lot more standardized, so we can just throw in a piece like we would in like RISA for a steel beam or something.
Yeah, these are too strange of shapes, so I don't think.
So
Yeah.
one last question for you, Chad. What do you see as the disadvantage of modeling things in RISA versus the Simpson program?
I think the Simpson program is just filling in fields, the RISA, you'd have to model everything out. I think the Simpson software covers 95% of every condition you're gonna capture, even if you break it down into numbers and whatnot.
It's simpler and
Yeah.
faster and easier to use.
Yeah, I guess if you get like, situations like a distribution header or something where you want to check the loads and what's coming into your studs, then something like RISA is great to have, or a 2D
Yeah.
beamer or something.
Very good. All right, any other questions? Nice job, Chad. Yeah,
Okay.
very nice.